We are now looking into this question, which forms part of fluid mechanics. The question says, in the figure, water flows through a horizontal pipe and then out into the atmosphere at a speed V1 is equals to 14.4 meters per second. The diameters on the left and the right section of the pipe are 7 centimeter and 3 centimeter. And then taking PO to be equals to 1.01 times 10 to the power 5 pascals, and the density of water to be 1,000 kilograms per meter cubed. The first thing first, in fluid, when solving questions in fluid mechanics, you have to state your assumptions. On the question, it is stated that the water flows through a horizontal pipe. When a water flows through a horizontal pipe, there is no any change in height. As a result, the elevation is negligible. So this will be our first assumption, that the elevation is negligible. It's negligible, meaning that it is very small. Okay, or we can say elevation. I wrote evaluation. Elevation. The elevation is negligibly small. So as a result, your age is just simply equals to 0. And then secondly, under normal conditions, like the pipeline in this case, and at a moderate pressure, like 1.01 times 10 to the power 5 pascals, water density doesn't really change significantly, even when subjected to varying pressures. Okay, the water density doesn't change significantly. Therefore, we can classify this water as incompressible. Incompressible, which means that there is no any change in density. And then thirdly, remember we are dealing with a flow in a pipe, right? Where the speed is constant at the specific cross-sectional areas. In this case being V1 and V2. Okay, in this case being V1 and V2. And there is no any mention on time dependency. Okay, therefore we can also conclude that the flow is steady. The flow is steady. So people, these assumptions, or I can say classifications, will allow us to use the principles that we just learned, the principle of continuity equation and also Bernoulli equation in solving the related problems. Okay, so now these are our assumptions. We are also given that V1. So this is what we are given. We are given that the velocity at the right section, it's equals to 14.4 meters per second. And then we are also given that the diameter on the left and right section of the pipe are 7 and 3. So therefore, your D1, it's equals to 0, it's equals to 7 centimeter, which is equals to 0.07 meter. And we are also given D2, which is equals to 3 centimeter. And this is equivalent to 0.03 meter. And then we are also given the pressure and the density. So this pressure is your P1 specifically. So that will be 1.01. So this is your absolute pressure at P1, times 10 to the power 5 pascals. And then we also have the density of water. So the density of water to be 1,000 kilograms per meter cubed. So this is the information that we have. And I believe we have enough information to attempt any questions that may arise. So let's look into the first question. The first question, it says the volume of water that flows into the atmosphere during a during a 5 minutes period. So in order for you to find the volume of water that flows into the atmosphere, so we have to use the continuity equations, right? Because the minute you are required to find the volume of water that flows, yes, the volume of water that flows, then you are basically required to find the volume flow rate. Okay, so it's important. The interpretation of question, it's very important in fluid mechanics, since it has many, many, many dynamics. Okay, it has it's very broad. Okay, so it's important that you interpret the question properly. So in this question, they are simply asking you to calculate the volume flow rate, but now they want it specifically for 5 minutes period. So we're gonna use the equation. Let me change the color of the pen. This yellow is not that clear. So we're gonna use the equation that the volume flow rate, it's equals to the cross-sectional area multiplied by V1 multiplied by V. So now we need to find the volume flow rate that flows into the atmosphere during a 5-meter period. So we can see that when we look into the diagram, the water flows into the atmosphere at the V1, and that is where we have the diameter D1, right? That is at the lid where there's an opening. Therefore, this means that we're gonna find the volume flow rate at what? At the right section of the pipe, okay, which is then going to be given by what? By the area on the right section of the pipe multiplied by the velocity on the right section of the pipe. Therefore, this is going to be R, and then sub V1 is equals to the area. So we have a circle there. Therefore, the area is simply given by pi r squared, and then this will be multiplied by V1. So this is going to be equals to pi. And then we are given the diameter. So the radius will be D1 divided by V squared multiplied by V1. So this is going to be equals to pi into our D1, which is 0.07, and then divided by our V, which is given to be 14.4. And then, no, I made a mistake. This is divided by 2. D1 divided by 2 because the radius is the half of the diameter. So this is divided by 2 and then multiplied by 14.4. So let's punch this on a calculator. Let's punch this on a calculator. We have pi, so that's gonna be shift, then 0.07 divided by 2, and then squared. I forgot to put squared, pi r squared, and then multiplied by 14.4, which is V1. And then this is going to give us 5.541, and then yeah, I'll just round it off to 3 decimal places, times 10 to the power minus 2, and then power minus 2, and then the units, this is going to be meter cubed per second, and this is the volume flow rate at V1 opening to the atmosphere. But now the question requires us to find the volume flow rate, specifically during a 5 minutes period. Therefore, this means our volume of water that flows into the atmosphere during a 5-meter period will be given by the volume flow rate, right? We calculated previously the volume flow rate and then multiplied by the time. So this is going to be equals to 5.541 times 10 to the power minus 2 meter cubed per second. Meter cubed per second. Okay, so then you multiply this by the time. Time is 5 minutes, and then in seconds, 5 minutes, it's 300 seconds. So let's see how much are we getting. This multiplied by 300, and then it's going to give you 16.63. 16.63 meter cubed, and that is the volume of water that flows into the atmosphere during a 5 minutes period. And then we are done with the first question. Let's go and look into the second question. And then on the second question, they say the speed of the pipe, the speed of water in the left section of the pipe, V2. So we need to find the speed of water in the left section of the pipe, V2. So we know that even here we have to use the continuity equation. So we know that by continuity equation, the RV is equals to A multiplied by V, which is then equals to a constant. So by definition, so this tells us that the volume flow rate at on the right section is equals to the volume flow rate on what? On the left section. Therefore, from this, we can conclude that our A1 multiplied by V1 is equals to A2 multiplied by V2. Then from this, what are we gonna have? We're gonna have that V2, which is what we are looking for. It's equals to A1 V1 divided by A2. Perfect. Then now let's calculate. This is going to be equals to, remember we calculated our V1, our A1, right? And we saw that our A1, it's basically pi r squared, right? So this is pi into 0.07 over 2 squared. So we're gonna substitute the same variable here for A1, that is pi. Forgot pi. And then this is 0.07 over 2 squared. And then we multiply this by 14. Let me erase this and rewrite it again so that I have enough space. So this is equals to pi, then into 0.07 divided by 2 squared, and this is multiplied by 14.4 meters per second squared, and then we're gonna divide this by the area A2. So that is going to be 0.03, and then divided by 2, and then this is also pi r squared, because even at the D2, right, this is a circle. This is the diameter D2. Therefore, the area is pi r squared, area of the circle, and the radius in this case it's 0.03 divided by 2. Then let's punch this in a calculator. Remember, this is pi. This is pi, guys. Don't get confused. So there's a shift to pi into 0.07 divided by 2 squared multiplied by 14.4. Then we're going to divide this by shift pi into 0.03 divided by 2 and then squared. And this is going to give you 78.4. This is going to give you 78.4. And this is the meters per second. And this is the speed of the water in the left section of the pipe. That's our V2. Okay, now we move on to number 3, question number 3. So question number 3, it says that we should find the gauge pressure in the left section of the pipe. Okay, so we know that the, let me write 3, the gauge pressure, which is the P gauge, it's equals to the absolute pressure and then minus the atmospheric pressure. Okay, but now if you can notice, the question says in the left section of the pipe. And in the left section of the pipe, we have D2. So that is P2, and we don't have P2. But P1, it is given as P naught there 1.01 times 10 to the power 5 Pascal. Thus, as a result, we have to apply the Bernoulli equation. Since we have assumed that our flow is incompressible and it is steady, the Bernoulli equation in this context will be more convenient to help us find the pressure at what on the pressure in the left section of the pipe. Now let's write down the Bernoulli equation. We know that using the Bernoulli equation, the pressure at 1 plus half by the density, the velocity at 1 squared plus P at 1 GH will be equals to the pressure at 2 plus half density V2 squared plus P2 GH. Okay, and remember the question stated clearly that the water flows through a horizontal pipe. As a result, we had the assumption that the elevation is 0. Hence, I mean, it's negligibly small. Hence, your H is 0. Now, since we have that assumption, already we can notice that we managed to eliminate these two last terms, right? Therefore, what are you gonna be left with? You're gonna be left with the fact that no, you're gonna be left with P1 plus half rho P1 plus half rho V1 is equals to P2 plus half rho V2 squared. Okay, so from this, we can make P2 subject of the formula. Now P2 will be equals to P1 and then plus we can take half rho as a common factor and we'll be left with, this is rho, my handwriting is bad, and then into V1 squared, forgot the squared here, minus V2 squared, perfect. And then that means our P2 will be equals to P1. We know the value is 1.01 times 10 to the power 5 pascals. Then this will be plus 1 over 2. This will be plus 1 over 2 into the density, which is 1000. And then this is multiplied by V1, which is 14.4. And then we square it minus V2, which we just calculated in the previous question. And it was found to be 78.4. Then we square it as well. So let us punch this whole thing on a calculator and see how much do we get. We have 1.01 times 10 to the power 5, and then plus the half of 1000, and then multiplied by 14.4 squared minus 78.4 squared. And this gives me minus 2.8. This gives me 2.8686 times 10 to the power 6 pascals. 6 pascals. Right. So this is our absolute pressure at the left section. Now we can continue and find our P gauge on the left section. So the P gauge on the left section will be given by P2 minus P atmospheric pressure. Then what do we have? Then we have and then we're gonna have P gauge to be equals to what is our P2? Our P2 we found it to be minus 2.8686 times 10 to the power 6. So we're gonna minus the atmospheric pressure of water. So what is the value for the atmospheric pressure of water? I think it's 101.325. I'm not sure. Let me confirm it. Let me confirm the value for the atmospheric pressure of water. Yeah, that value is 101.325 kilopascals. And remember, this is in pascals. Therefore, we're going to convert these kilopascals to pascals. So we're going to have minus 2.8686 times 10 to the power 6 minus 101.325 multiplied by 1000. And then that will convert it to pascals. As a result, our P gauge is equals to, let's punch on a calculator, minus 2.8686 times 10 to the power 6. And then this is minus 101.325 times 1000. And then this gives me minus 2.9699 925 times 10 to the power 6 pascals. So this is our P gauge on the left section of the pipe in terms of pascals. Now let's convert it to the atmospheric pressure, right? We know that 1 atmospheric pressure, we know that uh, we know that 1 atmospheric pressure is equals to 1.013 times 10 to the power 5 times 10 to the power 5 pascals. Therefore, our P gauge in ATM, our P gauge our P gauge in ATM will be equals to minus 2.69, no, not 6996, and then 9925 times 10 to the power 6 divided by 1.013 times 10 to the power 5. So let's punch on a calculator and see how much do we get. We have this and then divided by 1.013 times 10 to the power 5. Then this is going to give you, this gives me 29. This gives me minus 29.318. And this will be the gauge pressure in the left section of the pipe in terms of atmospheric pressure, ATM, minus 29.318 ATM. And that will be the end of the lesson. If you have any further questions, you can always come back and ask.